In this set of slides, we're going to begin our coverage of operating systems. We're going to work through this set of slides, and we're probably just going to cover the first handful of slides, giving a basic overview of operating system functions and a few key terms such as the various operating system layers. So, first thing to realize about operating systems is they haven't always been around, or at least they're not quite as old as modern computers are. Okay? And by modern, I mean digital computers, basically since the late 40s, early 50s. Okay? So if we look at an early computer system, there was no operating system. Okay, so if you bought a computer system in the late 40s or early 50s, chances are that it came with no software, nothing that would correspond to an operating system as we think of it today. Why was there no operating system? Well, let's look at the capabilities or lack thereof in a very early computer system. First, you're talking about a machine that, executed a few dozen instructions per second maybe, that had 2 kilobytes of RAM. Okay. Basically, there was only enough CPU and memory to execute one program at a time. Okay. So one simple program to say, read in a batch of cards representing account balances, read in a separate batch of cards representing, say, transactions against those accounts, do some basic calculations to apply the transactions to the accounts, and then punch out a new set of cards or maybe update a tape that represented the updated account balances. Okay. That was generally done in something called batch mode. Batch mode simply means, well, it means two things. One is it means one program at a time. The other is it means it's not interactive. The program does not interact directly with a user. Instead, it interacts with data stored in some sort of file, be it a stack of cards, be it a tape, be it a file on disk, okay, or multiple files. So you've got a machine that can only run one program at a time. There's nothing corresponding to interactive input-output as we think of it today. No keyboard, no mice, no video displays, no network cards, nothing of that sort. Okay. So the set of hardware resources was relatively simple. You had a CPU, one. You had a relatively small amount of memory. You had a really very little in the way that we would of devices that we would call secondary storage today. Maybe you had a tape drive that you could read or write to. Maybe it could read or write a stack of punched cards. Okay. The users who quote unquote used, actually a better word would probably be operate, that computer were highly trained, and basically they had to be because they were interacting with that computer at a very low level. Once again, no keyboard, no mouse, no point and click, no windows, no graphical display. Okay, not even a command language for those of you old enough to remember, such as something like MS-DOS or, say, one of the various command-oriented shells in Unix or Linux. Okay, nothing like that. If you were going to interact with the computer, you had a row of switches on the front, which basically represented, binary numbers, and to load a program, you stuck a stack of cards in that card reader. You went over and flipped those switches to a certain command. You hit a big red button on the front that basically said execute, and it would read in that stack of cards and load it into RAM. Then you'd probably flip those switches again to, say, the memory address of the first instruction in that program, hit that red button again, and bingo. Now that one program would basically take over the computer and run until it terminated. Okay, so the application program was all there was, whatever that program was doing. No operating system to deal with. So why did we wind up needing operating systems? Well, basically computers got better. And as they got better, their hardware got more complex. Their software also got more complex. And there became a need for a set of functions that today we associate with operating systems to basically make life easier. Okay. One of the big changes was the variety of hardware resources was changed. Okay, so things like disk drives came into play, where we could permanently store data on magnetic disk, and we didn't have to worry about loading and unloading tapes or putting in stacks of cards. We got printers, and then of course eventually we got other sorts of I/O devices. We got interactive I/O devices, keyboards and mice and things like that. The traditional sorts of hardware sources, say CPU and RAM, they became more numerous. So CPU, well, we didn't really see multiple CPUs for a long time, but we certainly saw much more powerful CPUs. CPUs that could execute hundreds of instructions per second, or thousands, or tens of thousands of instructions per second. And memory, slowly crept up in capacity. And eventually memory got to the point where, you could hold more than one program at a time in RAM. Okay. So that more powerful, that more complex, that more diverse set of hardware made for more powerful programs. The problem is those programs became increasingly difficult to write. Okay? And the reason they became difficult to write is because application programs at that time had embedded within them all of the instructions needed to directly control or interface with the hardware. So as the number of hardware devices increased and as their complexity increased, the complexity of the application programs increased, and similarly the job of an application programmer became much more difficult, because unlike application programmers today who really don't need to know a whole lot about hardware, application programmers of, say, the early 50s, they had to control the hardware directly. They had to write the instructions to, say, process an interrupt from a disk drive. Well, probably weren't disk drives in the early 50s. Process an interrupt from, say, a tape drive or a card reader. If they were going to, output to some sort of printing device, they had to execute very low-level control over that device. And so if you looked at an application program at the time, what you found is, as we move, say, from the beginning of the 50s towards the end of the 50s, the amount of code, the amount of instructions inside that program that were basically just there to deal with hardware control and interface issues kept growing and growing and growing and growing. Became a bigger and bigger chunk of the pie. All right, another major leap forward. Hardware became powerful enough to run multiple programs at the same time. So I've got dozens of kilobytes of RAM. I've got a CPU that can execute tens or hundreds of thousands of instructions per second. To simply have one program reading from one tape drive and updating another file based on some, some stack of cards or something that was reading off of a disk drive, that program would spend an awful lot of its time sitting there twiddling its thumbs, waiting for tape drives and disk drives and card readers and what have you to feed it data. So rather than have that CPU sitting there twiddling its thumbs, we stuff a little more RAM into that machine. We put two application programs in there, such that when one application program is waiting for input from the disk, another application program can sort of wake up and do something else. The problem with running multiple programs at a time is that you need to keep them from interfering with one another. So if I have two programs sitting, say, in RAM, in different parts of RAM, I want to make sure that program A doesn't, say, overwrite the instructions of program B. I want to make sure, for example, that program A and program B don't both try to send a page to the printer at the same time. And instead of winding up with, one page output from printer A or program A and the other from program B, I wind up with, half a line from program A and two characters from program B, and then, it ejects to a new page, and now I wind up with 3 lines from program A and then, another line from program B, so on and so forth. So if I'm going to have multiple programs running at the same time, they're going to share resources, but they need to kind of protect themselves from one another. And it's very difficult to embed that sort of code in an application program. So for example, imagine you're writing the part of an application program that outputs to a printer, but before you output at the printer, you gotta, write a piece of code that says, oh, well, go look and see if anybody else is using that printer. And if so, I'm going to sit here and wait a little while, and then I'll wake up and I'll go check again. And only if nobody else is using the printer do I then attempt to use it. And of course, if two programs were sitting there kind of waiting and they both checked at the same time but didn't see each other and they both start writing, you haven't really solved the problem. These sorts of algorithms and techniques used to exclusively allocate resources in a way that programs don't interfere from one another are fairly complicated. And if you try to put them in the application programs themselves, which early programmers did, now you wind up not only with a bunch of instructions in there that deal with hardware control and interface issues, but now you've also got them dealing with algorithms by which we avoid interfering with one another. So as you see, the programs get more and more complicated. Okay. One other issue. Programmers found themselves writing the same sort of code over and over and over and over and over again. So for example, if I've got a disk drive and I've got files stored on that disk drive, the basic code by which I say, locate a sector on the disk drive, issue a read command for it, wait for the disk drive to respond, listen for the interrupt, and then process the interrupt when it comes, and move the data from, say, the disk drive buffer into RAM. That sort of code is exactly the same no matter what program I'm writing that reads from disk. Okay, so that same subroutine, if you want to think of it that way, or function, is in every single program, or in most programs, over and over and over again. And there's lots of examples of this: reading and writing files stored to disk, interacting with printers, or in the modern world, say, opening a window or resizing a window or dragging a window on a screen, managing memory contents, okay, implementing buffers and caches to hold data on the way to and from I/O devices. Okay, these sorts of functions are used over and over and over again. And if you embed them in the application programs, in essence, you're rewriting the same code, or at least you're copying the same code and pasting it into a whole bunch of different programs. That becomes relatively inefficient. Okay, so it's these sort of problems: hardware complexity, hardware diversity, the allocation issues associated with multiple programs and how we give them resources and how we keep them from interfering with one another, and the need or the desire to avoid writing the same sort of functions over and over again is really the seeds of where modern operating systems come from. At least initially, what they were designed to do was address these sort of problems. Okay, so how does an operating system solve those sorts of problems? Well, it actually does that in several ways. Okay. First thing it does is it is the central point of control over hardware and software resources, especially hardware resources. Okay. So in a modern operating system, an application program doesn't quote-unquote talk directly to the keyboard. If it needs input from the keyboard, it asks the operating system basically for permission. Can I use the keyboard? And the operating system looks around and says, well, are there any other programs using the keyboard right now? And if there are, the operating system says, no, you got to wait. Okay. And if there aren't, then the operating system says, yes, okay, you can use it. And while that program's using it, if any other requests come, it will deny those requests, at least until the first program that requested access to the keyboard gives up control of it. So that's central point of control over hardware. It's also the central point of control over software resources. So for example, when I do something as simple as, say click on the start menu and click on an item in the programs, okay, that is telling the operating system, okay, I want to execute this program. So the operating system will then go out onto the disk drive, find the corresponding executable file, load it into memory, get it ready to run, and then basically hand control off to that program, or at least some control off to that program. And also just some basic housekeeping functions like installing new software or deleting old software. These are things that the operating system takes control of. Okay. A very important job, and we'll spend quite a bit of time talking about this, and the chapter certainly spends plenty of time talking about this, is coordinating access to shared resources. Okay, and same sorts of problems we talked about on the previous slide. Okay, if there are two programs in memory, the operating system will decide which one's going to run and which one's going to wait. It will protect them from one another. It will basically watch their memory accesses, and it will ensure that instructions in program A do not overwrite memory locations owned by program B, and vice versa. It'll coordinate access to things like printers to make sure that we don't wind up with interleaved lines of the output of two different programs in that printer. It'll make them basically take turns. Okay. Likewise, it'll coordinate access to any sort of shared storage, be that a file system or a directory structure on disk drive, be that a CD, be that whatever. Okay. Some other functions that it implements. Okay, here's one that we didn't think about a whole lot in the early days, but we certainly think about it today. Access controls and authentication. Okay, so I've got a set of programs, I've got a set of files sitting out there on a set of secondary storage devices. Which users are allowed to run which programs? Which users are allowed to read which files? Which users are allowed to write which files? Which users are allowed to access particular I/O devices? Okay. All of this control goes through the operating system. Okay, you can actually think of this as just an extension of the concept of central point of control over hardware and software resources, but it's more than just control in the sense of accessing, loading, running, whatever. It's control in terms of permissions. Okay, when we talk about access controls and authentication, basically we're talking about who are you. Okay, so username, password, for example, and once I know who you are, what are you allowed to do and not allowed to do? These are things that the operating system controls at a very basic level. Okay. Last thing that the operating system provides is a set of utility programs, okay, that will perform functions needed by many different application programs. So for example, managing I/O buffers for reading or writing to or from, say, the keyboard or the screen. Providing functions to read, open files, read files, write files on a disk. Provide functions to interact with the network, grab me a packet, send a packet. Okay. When we get into interactive, it will provide a set of functions, often which come under the heading of look and feel. Okay. Why is it that every Windows application looks the same? Why is it that every application on a Mac pretty much looks the same, has the same sorts of controls and features? It's because those controls and features are buried in a set of utility programs that were installed when you installed the operating system. The application program doesn't reinvent those, it simply reuses the ones that are already in the operating system. And since all the applications are using the same set of operating system interface functions, they all tend to look and operate the same. Same sorts of things you do to, say, resize or minimize a window. Okay, so reviewing quickly, central point of control over hardware and software resources. That's both things like execution as well as housekeeping functions like install and delete. Expanding a bit on that, access controls and authentication. Coordinating access to shared resources, allowing multiple programs to run, but in a way that they don't interfere with one another, and providing those application programs with a set of utility functions to do things that many or most application programs need to do, thereby saving the need to rewrite or reinvent that wheel in the application program, and also providing some consistency in the way those application programs function. Note that this issue of providing utility programs and central point of control pretty much go hand in hand. Okay, it's very difficult for the operating system to maintain, say, control over reading and writing files to disk if it's not providing the utility programs that do that. Okay, if the operating system starts allowing application programs to do their own reading and writing to disk, then how is it going to maintain that central point of control? Whereas if all of the disk I/O that application programs do are funneled through the same set of operating system utility programs, then those utility programs can themselves be either directly or an interface to some code that serves as the central point of control, coordinates the access to the shared resource, etc., etc. So really, this issue of central point of control and coordinated access is really not, you can't really do that unless you provide a set of utility programs to perform related functions for those shared resources or shared hardware devices. Okay, so let's talk about the pieces or the layers, as we'll say. So one way to think about the operating system is as a series of layers, and you kind of think of this like layers of the onion. And at the core of the onion is the actual hardware. Of course, we've just got it drawn as kind of a circle here, but clearly there's much more to hardware than just one thing because there's lots of different hardware resources. Outside the onion is the user that's either interacting with an application program or interacting directly with the operating system through one of its layers. Okay. Moving from the hardware out, the first layer or ring that surrounds the hardware is called the kernel. And the kernel has two basic jobs. Job number one is to interact directly with the hardware. So any sort of control over hardware, any sort of interface with hardware comes from software that's in the kernel and issues instructions to the hardware. Okay. We can sort of decompose that hardware interface piece into one part of the kernel per hardware resource, and that part of the kernel is a device driver, which we'll talk about more on the next page. Looking at the set of hardware resources as a whole, there's also a piece of the kernel that's concerned with allocation. Okay, allocating hardware resources to users and programs and controlling access. So, which user gets to interact with the keyboard, or which application program gets to interact with the keyboard now versus which one's got to wait. Or say when a packet comes in from the network through the network interface unit, looking at that packet and saying, oh, that packet is going to the web browser, or oh, that packet's going to the web server, or oh, that packet's going to this particular application program, and routing it. So the kernel deals with those sorts of allocation, control, access, it's all those sorts of words that cross the set of users and programs that are currently interacting with the system. Okay. Moving one layer out from the kernel, we come to the service layer. And earlier we described this set of utility programs that application programs use to do things like read and write to the disk and interact with the graphical user interface. We said that the two advantages to having those programs. One is by having the programs available, we don't have to rewrite that code in the application program, and that also by having those utility programs available, that sort of funnels all the hardware access through those utility programs, which enables the operating system to be that central point of control, be that coordinator and access control point over those shared resources. So that second layer, that service layer, is in fact just that big old set of utility functions. Think of them as methods or functions or subroutines or whatever name is used in whatever programming language, if any, you have any familiarity with. Okay, but what they really are is just a set of relatively small software functions to do very specific tasks. Read a file, write a file, copy a file, delete a file, send a packet on the network, receive a packet from the network, open a window, close a window, resize a window, so on and so forth. Those are the kind of things that service layer does. Now the last layer out, and moving out to this outer ring, if we look down on the bottom, we see here in white are application programs, which are not technically part of the operating system, but basically an application program does most of its work. Oops, let me change that. An application program does most of its work by talking to the service layer. Okay, so it'll send a request to the service layer, say for example, open this file and read me the first thing that's in it. The service layer will in turn interact with the kernel, okay, for things like, am I allowed to read that file? Okay. Will you allocate me some buffer space for I/O to and from that file? Okay. And then when it's time to actually issue, say, a read command directly to the disk drive, the kernel will implement that directly through one of its device drivers. Okay. So there's this kind of sequence of one layer calling another. So the application program calls the service layer in turn calls one or more functions in the kernel. Each of those functions in turn interacts directly with whatever hardware devices are needed to satisfy the request that initially came from the application program. Okay, so this is the concept of software layers. Okay, now the outermost layer of the operating system is shown here on this top part called the command layer. So sometimes we have an application program interacting with the service layer. But there are some things for which we don't have application programs, but they're sort of housekeeping tasks or what have you, that where the user needs to directly interact with the operating system. Now, we don't want to have the user interact with the operating system by making subroutine calls or function calls. We would like the user to interact with the operating system in a way that's fairly natural. Okay, so for example, in a graphical user interface, we point and click. So if I want to minimize this window, I come up here and I hit that little spot, and bingo, the window minimizes. And if I want it to come back up, I come down to the taskbar, which you can't see because that's not on my recording spot at the moment. And I click on that thing down at the taskbar, and bang, it opens back up. And I can drag it around, or I can resize it, or whatever. Okay, there's a portion of the operating system called the command layer. In this case, you'd probably call it a window manager, that's responsible for these sort of functions. As a user, I'm directly interacting with that command layer, but that command layer in turn is talking to the service layer. So for example, when I click that minimize button right up there, if I were to click on that, the command layer captures that keystroke and it makes a call to a service layer to a function, say, called minimize window. And it passes in as one of the parameters of that function which window of the various windows that might be open did the user click that command for. The service layer will in turn call the kernel. The kernel will provide access to, say, the graphics card in order to do that. And once that window is minimized and I've got to redraw the screen in order to show what used to be underneath of that window, that's going to be interacting directly with the hardware. So that kernel is in turn going to talk to the hardware directly. So just as with the application program, there's this layering of calls. User interacts with command layer calls one or more service layer functions functions interact with the kernel to get access to the resources. Kernel, when it actually needs, when some actual hardware function needs to be performed, interacts directly with the hardware via one of these device drivers. Okay. Now, with respect to the command layer, there are various types. Most users today are only familiar with one type, and that's the graphical type. So mouse, point, click, or, finger on a touch screen sort of deal. Use a keyboard when you have to, be it an actual physical keyboard or be it a virtual one that pops up on your touch screen. Okay. But there are other types, the primary other type being what's called a command line or textual command layer. So for example, let me show you an example. Okay. So here's an old style DOS command layer. Okay. I've got a prompt here, and I actually type in commands. So for example, say I want to list out the files that are in this directory C users bird. I type in dir and I hit the enter key. And there's a list of the files and directories that are in that. If I want to change the current directory, say to, I don't know, let's pick one here, 452. I type in cd space 452, hit enter, and now I'm in the 452 directory. Okay. So on and so forth. Okay, so there's a series of textual commands that I would enter from a keyboard. Okay, and textual response that comes from that. So this is one way of controlling a computer, rather old-fashioned way in the point of view of most students, but it's a way of controlling it. Okay. But another way, a more modern way, is opening windows, dragging windows, right-clicking, left-clicking, pulling down menus, so on and so forth. Okay, both of those are alternate ways of interacting with both an application program and with an operating system. And operating system today usually supports both, although you tend to use the graphical one. We could also imagine voice input. Okay, so we could imagine a command layer which is voice based rather than text-based or point-and-click sort of based. Okay, so it might be possible that there's actually several different command layers in the same operating system, and you use one some of the time, but you use others at different times. Okay, so anyway, that's the concept of a command layer. All right, move on to the last content slide before we take a quick break for an exercise here. Let's talk a little more about the kernel and the device drivers. So as we said on the previous slide, we can really think of the kernel in two ways. Way number one is as this resource allocator. Okay, so if the application program or the command layer made a particular call to the service layer, for example, list the contents of, tell me the names of all the files that are in this directory, for example. Okay. That service layer routine that performs that will interact with the kernel in order to get access to whatever resources it needs. Well, what resources does it need in order to list all of the files in a directory on the disk space? Well, it needs to read the directory, and the directory is stored on the disk, so it's going to have to interact with the disk. Once it interacts with the disk to read the names of all the files out of the directory, then it's going to have to display them to the user somehow. So it's either going to have to open up a window, or it's going to have to print out a list to the printer, or so on and so forth. So there's typically, well, I shouldn't say typically, but often there's multiple resources that need to be allocated. In this case, there's access to the disk, there's access to the screen, or to whatever output device is going to display this list. Okay. So the first job of the kernel is to decide what resources are going to be needed. Okay. A, do they exist? B, is anybody else using them right now? Do I need to make this request wait until some other user has finished using the resource? Or is the resource free right now and I can go ahead and do it? The second piece, or pieces, of the kernel are basically a series of interface programs, one per hardware device. Okay. And I've got a series of them here, which is certainly not complete, but it's close enough. So for example, there's a video display device driver. Okay, this is what controls what's currently being displayed on the screen. There's an interface program for the keyboard. As you can imagine, the interface program for the keyboard is probably a little simpler than the one for the video display, but nonetheless it's a separate program. There's another one for the mouse. There's another one for the disk drive. Okay, there's another one for the CD drive or the DVD drive. There's another one for the sound device. There's actually probably multiple ones for the sound device. There's one for incoming sound, say through a microphone like I'm doing right now when I'm recording this. There's one for sound output, say through a set of speakers. Okay. So basically, as many devices as there are in the system, there are at least that many kernel device drivers, and possibly more, because sometimes there are multiple device drivers associated with the same device. Okay. So device drivers are basically the bridge between the service layer and the hardware devices. Okay. Device drivers, they do a number of things besides, or in addition to the actual interface. One is they implement the interface in a way that access to devices of somewhat similar types all sort of quote-unquote look the same to the service layer and to the application programs that use them. We'll come back to this later. This isn't something I really want to spend any time on now. Okay. One of the advantages of organizing the kernel as a resource allocation layer and these series of device drivers is that to the extent the device drivers are independent pieces of software, they can be updated. Okay, and they can be done so generally without changing any of the other operating system or application components. Okay. What's the advantage of that? Well, there's a couple of situations. Okay, let's take situation number one. Let's say my hard disk is too small, and I come along a little later and I want to put in a bigger one. But that bigger one uses a slightly different interface. Say, SATA version 1 is now SATA version 2. Well, my hardware, okay, my computer motherboard or whatever, wasn't necessarily originally designed to talk to SATA 2 drives. Maybe it was designed back when there were only SATA 1 drives. So how do I enable it to talk to SATA 2 drives? Well, I update the hard disk device driver, and I update it in such a way that the new device driver knows how to speak whatever language is spoken by a SATA 2 hard disk. Okay, so that's one example of a way in which this device driver approach enables an quote-unquote old operating system to be updated to newer hardware. Now you can take this a step further. Maybe there's a piece of hardware that didn't exist in the past, but somebody invents, and you decide, well, gee, I want to put that piece of hardware on my machine. So say I can't really think of something offhand. Let's say there's some brand new kind of game controller that it's not a joystick, it's not a mouse, it's something you stick on top of your head and it reads your brain waves, okay, directly, and that's how you move. That's how you move back and forth in a game, simply by thinking where you want to go. Okay, well. Probably, let's say we're talking Windows 7. Well, when Windows 7 was designed, there was no such I/O device. But now I want to take a computer running Windows 7 and I want it to use such an I/O device. Well, maybe I hook that up through a USB port or a FireWire port or something like that. But the device itself is unknown to the operating system. But if I install a new device driver, okay, and if that device driver operates in a way that is at least similar to some other device in the system, say I make it similar to a keyboard driver or a mouse driver or a combination of the two, I don't know, then it's possible to extend the capabilities of an operating system to a new class of hardware that didn't necessarily exist when the operating system was originally designed. Okay, so basically what we're after here is flexibility. Okay, this device driver approach gives me flexibility to improve existing device drivers or to add brand new device drivers for brand new pieces of hardware that nobody even thought of back when they developed this original operating system. Okay, and that flexibility is very important unless you want to be throwing away your operating system and your device every 6 months or a year or 2 years because there's new hardware capabilities that you can't embed in them. Okay. Most cases we like our devices to live a little longer, maybe not cell phones, but certainly desktop computers and servers and things like that. We'd like them to live across a generation or two of hardware, and this device driver approach is one way of enabling that. All right, so going to the last slide, there's a very quick exercise here concerning these device drivers. If you're on a Windows computer, you can go to either the Start button and look at My Computer, or if you're like me and you've got it sitting on your desktop, here I'm going to copy it right there. Oops, I can't seem to get it out of there. Okay, so there's My Computer. Okay, I'm going to right-click on it and I'm going to choose Properties, and up pops this particular screen. And over here under Control Panel Home on the left side at the top is a option called Device Manager. Let me go ahead and click that. And that will open up this window here. Okay. And basically what this shows me is my computer and a listing of the types of devices attached to it. Now actually I have mine being displayed by type. You can also display them by connection, as we did in an exercise in a previous chapter. Okay. But here we're doing it by type. So note some of the types here. We've got Bluetooth radios, we've got display adapters, we've got DVD and CD-ROM devices, we've got imaging devices, keyboards, mice, old-fashioned I/O ports, COM ports, and LPTs. We've got the processors themselves. I've got a quad-core processor on my machine, sound, video, game controllers, storage, so on. So we've got them basically listed here by type. Now let's come back here for a second. So I wanted you to expand the category sound, video, and game controllers. Okay, and that is this one right here. So I'll click just to the left of it, and you'll see I have two sound, video / game controllers on my machine. One is this Microsoft LifeChat LX3000, which is a headset. It's the one I'm using to record this video on. And the other is just called High Definition Audio Device, and basically this is the sound card that has the speaker out and the record in and the line in jacks on the back of my computer. Now if I right click on this High Definition Audio Device and choose Properties, okay, I see it's of type sound, video, and game controller. This was manufactured by Microsoft. Actually, that's pretty unlikely. Okay, it's on the high definition audio bus, but the one thing I want to concentrate on here is the device driver, which is this middle tab. Okay, the device driver software was written by Microsoft. The date that was written was November 19th, 2010. This is version 6.1.7601.17514. Okay, and note there's some functions here to update the driver. Let's go ahead and hit update, and I'm guessing it's not going to find one, but we'll let it look for a little while anyway. So it's now searching online to see, okay, is there a later version of a driver that will talk to this? And apparently not. Windows has determined that this device driver is up to date. But if there was a newer one that, say, either fixed some bugs or added a couple of new features that weren't present in the original driver, it would have found it and either installed it automatically or asked me if I wanted to install it. And that would have updated the capabilities of this device. If I look at the driver details, here are the actual files and their locations that are this driver. So this driver is actually a piece of software that's spread out, as I see, across 7 different files, and probably, but not always, you can think of each of these files as implementing one function that device performs. Because a sound card can actually perform several different functions. It can record, it can it can send out to speakers, it can record interact with a microphone, so on and so forth. Typically there's going to be multiple pieces of the driver stored in various places, various files here. So this concludes our discussion of device drivers and our quick introduction to operating system layers and functions. We'll pick up in another video with other topics associated with operating systems.